Hi everyone. Today I am going to talk about big field, limit of infinite derivative gravity. This is my outline. In introduction, we will discuss why we need to modify Einstein's gravity, and then I will give a brief introduction to infinite derivative gravity. And after that, I will calculate the scattering amplitude between two spinning sources that also have velocities and orbital motion. And then I will find the corresponding potential energy, which includes Newtonian potential energy, spin-spin interactions, and spin-orbit interactions. And I will finish my presentation with conclusions. This talk is based on the following two papers, especially the first one. In the second one, I constructed exact PP-based solution of the theory. And field equations for this theory are very lengthy, highly nonlinear, and complicated. And therefore, finding an exact solution seems hopeless. But if you write the metric as a Kershel form, you can find the solution. It leads to remarkable simplification in finding solution. But today I will talk about the first one. Although Einstein's gravity solved many problems in Newtonian physics, it suffers from two main problems. The first problem is that we have not quantum gravity theory. It's not perturbatively renormalizing. And also, at the classical level, it has cosmological and black hole type singularities. And this is a problem. This problem is related to small scale. And then the second problem is that GR does not give explanation to the acceleration expansion of the universe and rotation curves of galaxies. And this problem is related to large scale. And today I will consider the small scale modifications of the theory. And with modification, I mean, for example, if you add to the Einstein's theory, this Einstein's Hilbert action, if you add some higher curvature terms to the theory, in this case, this is called quadratic curvature gravity, theory is renormalizable, but unitarity is lost. And in fact, there are many modifications of Einstein's gravity, but among the small scale extension of Einstein's gravity, infinite derivative gravity seems to be natural. Why it seems to be natural one? Let us discuss. This is the Lagrangian density for infinite derivative gravity. And this is the Einstein term, and Einstein's gravity is modified by other terms. And this Lagrangian density is coming from general covariant action. And in here, F1, F2, and F3 are the functions of box operator or the D'Alembert operator. These are the functions of infinite derivative. And okay, I forgot to say. Here, M is the mass scale of non-locality, at which non-local interactions becomes important. And this theory has nice properties. For example, if you look at the propagator of the infinite derivative gravity, this is the propagator. And if you look at this propagator, the second part describes mass spin to gravity. This is the propagator for Einstein's gravity. And the extra pose can come from this function A. Here, K is momentum space wave factor. Here, A can be written in terms of form factors, F1, F2, and F3. We will see. And I said that extra pose can come from this part. However, if you choose A of minus K squared to be an exponential of an entire function, in this case, this function has not any rules, residues or pose. And then theory has only mass spin to gravity, but it is propagated exponentially suppressed by this function. And therefore, vortex factors are exponentially enhanced. And since theory does not have any extra degree of freedom, it is free from ghost-like instabilities. And it has improved behavior in the small scale. For example, up to 2 loops, the ultraviolet divergence can be eliminated in the theory. For higher loops, some works claim that divergences can be removed out by direct propagators. And also, power counting arguments show that this theory is superly normalized. And another nice property of the theory is the Newtonian potential. If you calculate Newtonian potential for this theory for point-like source, we can get this potential. You see that Einstein potential is modified by error function, this error function. And if you go to the large distance limit, as r goes to infinity, error function goes to 1, and we recover the pure GR limit. We obtain minus Gm over I. This is the Newtonian potential for Einstein's theory. As this is the expected result. On the other side, at the small distance, as r goes to 0, error function approaches I. And in this case, we have this potential at small scale. And this is the constant. It approaches to a constant. And unlike the GR case, in the Einstein's theory, this term diverges according to 1 over I. And it becomes singular. This theory, this solution is non-singular. And therefore, infinite derivative gravity may resolve the problem of singularities in black hole and cosmology.
By the way, do you have black hole solution in this theory before resolving singularity?
Yes.
Do you have?
For example, in
Does
I don't have, but some.
Does such a solution exist in this theory, black hole solution?
Yeah, yes. There are also, we know some solutions, some non-singular cosmological solutions.
Black hole solution.
Yes, it's black hole solution. For example, in my last work, I found, it's not black hole, but I found non-gravitational shock wave solutions, and it's non-singular. Okay, you are asking black hole. I know, yeah. You can look at the literature before last week, Mazlumdar.
Last week.
I think last week or 2 weeks ago, I'm not sure. Mazlumdar published a non-local star black hole. You can check. There are some black hole solutions.
Yeah, I know both of them very well, Mazlumdar and Modest.
Yeah, this was, yeah.
As far I know, I don't know what happened last week or last 2 weeks, but there was no black hole solution in this.
You can check.
Okay.
Okay. Yes, okay, I forgot to say. In this work, I would like to this discussion to include spins, velocities, and orbital motion of the sources, in addition to point source. And for this purpose, I will consider the Lagrangian density for the infinite derivative gravity, and at linearized level, field equations can be written in equation 7 here. A, C, and F are nonlinear functions, and they can be described in terms of form factors F1, F2, and F3. And in fact, here I have 2 options to have ghost freedom. First option is you can choose A is equal C. In this case, theory has only mass spin 2 degree of freedom, like Einstein's theory. Also, you can choose A is not equal C. In this case, theory has extra mass spin 0 gravitons, in addition to mass spin 2 gravitons. In here, I will choose this condition, since this condition is giving a clear path back to GR. I want to compare the results, GR and infinite derivative gravity. Therefore, I will choose this condition. In the Dedonder gauge, linearized field equations takes the following form. Here, G mu L is linearized Einstein tensor, is the source. I want to calculate scattering amplitude. To calculate scattering amplitude, we need equation like operator times field is equal source, like wave type equation. If you take the trace of this equation and using the linearized form of Einstein tensor, we can obtain this equation. This is the desired form. Operator times field is equal source. Now we are ready to calculate scattering amplitude. Before going into further details, we know that H mu nu has 10 components in 4 dimensions. All the components of field are not physical, and therefore we need to eliminate non-physical degree of freedom. And for this purpose, we will decompose the spin 2 field in terms of tensor, vector, and scalars. If you put this decomposition into a wave type equation, we can get this equation. Here, O minus 1 is scalar Green's function. If you look at this scalar Green's function, you can see this is the modified Green's function. Modified Green's function. This is the picture for 3-level scattering amplitude between 2 sources via 1 graviton exchange. And from this picture, we can calculate scattering amplitude using this formula. If you put the decomposition of field and source, finally we can obtain this equation. Now, if we have source, we can calculate the scattering amplitude. Here, for the sake of simplicity, I have suppressed the integral sign. And now, as I say, I want to calculate the scattering amplitude between 2 spinning sources that also have velocities and orbital motion. And for this purpose, I will consider the following energy momentum tensors. Here, this is the point-like source. Here, MA are the masses of the particle, VA are the velocities of the particles, and JA are the spins of the particles. And if you put this energy momentum tensors, scattering amplitude equation transform into this form. And now we can calculate the scattering amplitude. We need one more thing. We need to find the scalar Green's function. As I said in introduction, A in here, function A must be an exponential of n-type function to have ghost field. And the simplest choice is e to the minus box over m squared. Here m is the scale of mass scale of non-known value. And the Green's function can be calculated as in equation 20. If you go to the large distance limit, Green's function reduces to 1 over 4 pi times Dirac delta. This is the Green's functions for Laplace operator. Okay, if you put this Green's function in here and taking the integrals, finally we can get the following potential energy. Here, the first term is Newtonian potential energy, the others are relativistic corrections, second line and third line show spin-spin interactions, and fourth and fifth line shows spin-orbit interactions. Here, I want to find the behavior of potential energy at the small scale. And before that, for large separation, as r goes to infinity, the potential energy takes the following form. And this is the Einstein's result. Okay, on the other hand, for the small distances, as r goes to 0, the potential energy takes the following form. You see that at the origin, potential energy is non-singular, and it approaches to a constant. This good results. Why it's good result? We started, the potential energy is generated by sources. These sources contain Dirac delta type singularities. But at small distances, potential energy is non-singular. And we show that not only the usual Newtonian potential and also the spin-spin and spin-orbit interactions becomes non-singular at the origin. For example, for Einstein's theory, this is the spin-spin interactions term. For the Einstein's theory, this term diverges according to 1 over r cube. It becomes singular. In this theory, it's constant. And therefore, this theory is much well behaved in the ultraviolet region when you compare GR. And as a conclusion, we compute the three-level scattering amplitude in infinite derivative gravity and found weak field potential energy between 2 point-like spinning sources that interact via one graviton exchange. We showed that the spin-spin and spin-orbit interactions take the same form as in Einstein's gravity at large separation, while at small separations the results are different. It's important to note that not only the usual Newtonian potential energy, but also the spin-spin and spin-orbit interactions terms in the potential energy is non-singular at the origin. Okay, thank you.
You have one question?
Yes.
There can be some misunderstanding about the jargon, so I should stress this first before asking my question. So you talked about form factors
Yeah.
In your expansion. So,
Like QCD.
okay, so there's no problem with the jargon.
No.
Then, for example, if you think of two protons scattering off each other, they have form factors, and for example, you can calculate their photon exchange, or you can calculate their graviton exchange as well. But the binding forces are non-gravitational or non-electromagnetic, so they are independent problems. But here, you are calculating the one graviton exchange amplitude for two masses, and if they have form factors, they have substructure, they are bound states, and they are most probably bound by gravity, and that should impose some conditions maybe on your expansion or on your theory. So, how do you comment on this?
Also, I forgot to say, this theory is asymptotically free. For example, we have potential energy. If you calculate the force gives 0. It's asymptotically free. Okay?
At this order,
Sorry?
at this order, right?
At this order, yeah. Okay? Like QCD. And here, I am neglecting some terms, order V squared, J squared, since I am using Newtonian approximation. Okay?
Thank you very much.